what is the relevance of this Fourier series or these expressions in terms of data communication? Because when we are dealing with real channels, actual communication, different frequency will be affected differently. That is, data communication, real channels affect different frequency signals in a different manner. For understanding this, let us take an example. And we will take an example of actual transmission of bits. For example, you are trying to transfer, say, a character B. Now the ASCII character B we want to transmit. We know that the ASCII value of small b is 98. So we will encode it in a 8-bit byte. So that will be 0110010. I'll just try to calculate and tell you that this is 98. So this is 2-bit and this is 32, 64. Now just add 64 plus 32 plus 2, you get 98. So this is what we want to send. This is a proper bit pattern. And the whole idea is this bit pattern has to be in the formation of sine and cos we have to send. And we have to retrieve as well. So this is the actual binary signal which we want to send. Okay, this is computer is transmitting. A digital device is transmitting and it is nothing but just a voltage. Please remember, it is just voltage. So what will be the Fourier analysis? What is the Fourier analysis result? So the coefficient, that is the A sub n, B sub n and constant will come like this. Now how do we get this? This is a very big question. I'll just give you a basic hint. How do we get this an and bn? It's a another science or aspect of mathematics that will take a long time. But I'll just give you an idea. How do we achieve these expression an and bn? So first of all, you have to understand we are dealing with 8 bits here. So let me write bit here 0, 1, 1, 0, 0, 0, 1, 0. These are 8 bits. We are trying to send b. Now what are the constants? an, bn and cn. The constant is, the expression is, the formula is n by 4. N is the number of ones in the byte, regardless of the position. So how many ones are there? 1, 2, 3. 3 ones are there. So 3 by 4. You got the constant? Now let us come to an and bn. We already have a formula. An is 2 by t integration 0 to t gt sine 2 pi nft dt. Same for bn. Now the function is gt. This is 8-bit. So I am going from 0 to 1, 1 to 1, 1 to 0 like this. So from 0 to 1 we can easily assume that this is a piecewise constant function. What I am trying to say here is that we have to find out gt. What is the gt? When I am saying I am going from one place to another, from 0 to 1, it can be 0 to 1, it can be 1 to 1, it can be 1 to 0. So it will be a straight line. So it's actually a piecewise linear constant, a piecewise constant. Because I am not going to integrate from first bit till 8-bit. I am going to integrate from first bit to second bit to third bit to fourth bit like this till 8th bit. Right? So basically gt is a constant. If we just take one bit, it is constant. So we will integrate it and assume that this function gt is nothing but a constant. So there is no gt now. Okay, now we know the expression of an and bn. So there is one term you have to understand, that integration is from 0 to t. But this is for whole time period. But we are talking about 8-bit. So how to divide this 8-bit into time period? So we are introducing this kt by 8 till k plus 1 t by 8 because k is varying from 0 to 7. 0 to 1, 1 to 1, 1 to 0, 0 to 0, 0 to 0, 0 to 1 and 1 to 0. So that is why gt is constant and we integrate it from kta by 8 till k plus 1 t by 8. First with the cos term, second with the sine term, you know the integration. You know sine and cos integration. Finally, when you put the limits, you have two expressions for an and bn. A sub n and ba sub n. Right? I hope you got a basic idea. I'm not going into the detail. This is how we get an and bn. Now this constant, or you can say the harmonics, the final term is we have not achieved because the actual byte is B we have sent. So there are 3 ones here, 1, 2, 6. So now you have to put n equals 1, n equals 2, n equals 6, and then you have to add. So put 1, n equals 1 in both. I'm just telling about B and say k equals 1, you have k equals 1, not n, k equals 1, k equals 2, k equals 6, and then you add them. Finally, you will get the actual harmonic or the coefficient or the Bn term. Similarly, you will do it for the other one, you will get the An. So this is how this has come. I hope you got the idea. Now we have got this A, B and C, that is the coefficients and the constant. These are nothing but the harmonics also. But how to represent these in terms of actual value? Let us say we are putting n equals 1, that is A1 and A1 and B1. So when we are putting n equals 1, this is the first harmonic. So A1 we are finding, A2 we are finding, we are squaring it and adding it and taking under root. That is the root mean square amplitude. So the root mean square amplitude, this is the first harmonic, which you see in the figure also. Now let us take n equals 2 in A and Bn. Now when you put n equals 2, then you will square them, add them, take the square root. So let me show you here. This is the A1 plus A1 square plus A1 square plus B1 square under root. This is the first harmonic. Second one is A2 square plus B2 square under root. This is the second harmonic. Okay. So the square of these values, which I just told you, they are proportional to the energy transmitted at the corresponding frequency, at different frequencies, right? No transmission can transmit signal in any channel without losing some power. Without losing power, it is impossible. So if all the Fourier components, which we are calling it as A and Bn, they were equally reduced, the resulting signal will only be reduced in the amplitude, but they will not be distorted. They will not be distorted. The shape remains same. This is how we send. I will talk about actual bit, how many harmonics we need to send this bit formation. Okay, because we have to limit. There can be multiple harmonics. You can argue that it can be A1 till A infinity. But how many harmonics do we need? Before that,